Okay, okay. So for this last lecture, I changed a little bit my mind over the weekend. So I uploaded the slide updating over the weekend. Um, yeah, I wanted to mention about CP violation, but obviously a lecture of CP violation in 1 hour is a bit ambitious, but I thought it was also important to mention all the measurements than the one we were talking about, the rare BDKs. And I thought also it was interesting to see the perspective of Indian Belle II group and involve their measurement in the lecture and see actually how much the flavor physics can cover, and how much Indian colleagues have been involved. So I think for the students of India, it's also important to understand that there is a, you know, living active Belle II Indian community. So either you are future experimentalist or theorist, as you can see, I mean, you can find people already in India involved in Belle II, in Belle and Belle II, and can start to discuss about physics, your main interest, and see how much can be measured, because this is kind of a unique opportunity for young physicists, and those, as you have seen, don't come that often. I mean, in some sense, Guy was, right to mention all the attempt of even in flavor physics, and we always talk about the successful experiment, of course, and whereas it's important to see that actually also sometimes we have a experiment working not as good as expected, and consequently we should of course, as he said, respect the people working on it, and often that helps the next generation, but also appreciate when we have something ongoing. So Bell and Babar as LHC were quite successful in their program, physics program, and for Bell to, well, the jury is still out, and the data are just coming. So in few words, I summarize in a couple of slides. We were, during these 3 lectures, I think we were talking about, I think here are in one slide, the keywords: energy frontier versus intensity frontier. Energy frontier was supposed to bring us to the promised land, but the physics decide, not us. And consequently, intensity frontier keep its mission of being maybe the first to point where the new physics could be, and consequently help future generation to build what is really needed to discover measured new physics. But yeah, for the time being, we are a bit in the dark. So the goal are to accumulate as much as luminosity and to measure things as precise as possible. I mentioned rare decays as a kind of, well, the second and third category, either in some sense, some precision measurement to do now in loop. For B2S gamma, this already has been done, or I mean, in part, in large part, will be improved only with more statistics. And for some more suppressed decay, like the one I mentioned, B2SLL, or here B2 mu mu, and so on. I mean, those are ongoing, and the measurement is still not as precise as we need, but yeah, it's getting there. And the even more interesting part is that there is some exciting hints of Lepton Non-Universality, so breaking this ratio, this famous RK star. And you will get some very nice lecture, I'm sure, from Jure today and tomorrow on the subject in the theory point of view. So here, I just mentioned that, okay, to explain those anomalies, those seen in B2S, but also the one I mentioned we call RD star, which are in B2 D tau nu, D star tau nu. Some model are favored, or at least put in, I mean, sort of us to explain those, among them the leptoquarks. And after, let's say, kind of tuning those model from the measurement we already have, the theorists give us a bunch of prediction or possible avenues where we will look for confirmation, either by you know, those mod with the third generation. So we have this effect which seems to be generation dependent, of course, because the mu versus EE, and then enhance would be enhanced in the third generation. So you look for mode like, you know, B2SLL, but where the leptons are tau, so which will be enhanced compared to the standard model. And we explained last time how they will be measured. And in some sense, this third category even more interesting in the sense of they are, you know, a clear sign of new physics if observed, if only observed, where you have two leptons in the final state, but this time of different flavor. So we talk about K tau mu, following the same, you know, method, experimental method analysis method to extract the signal with missing energy in the final state. We were talking about the B-tagging, and the also I didn't mention the KMUE. I mean, that's also some effort we have done. Here the prediction is much lower, but the sensitivity is actually much better because you have a two lepton easy to reconstruct in the final state, so very similar to KMUE and KEE. Okay, here I'll make a little pause, in fact, and unfortunately, those virtual meetings don't allow, you know, the most important part of the exchange, or at least an important part of the exchange of this kind of school is the possibility to interact during, you know, tea break. I was about to say coffee break, but also tea breaks. And then interact with actually people who contributed, people who are still contributing or working on those sector, especially local people, and which will allow, in fact, as I was saying, this exchange of, you know, between theorists and experimentalists, or people interested by doing those measurements to join the effort. So here, I hope, you know, in this case, I was anxious to not forget any institute. I did my best to list all the institute involved in Belle II and Belle, actually, and you know, the leader of each group that most of you probably know already. And as you can see, Belle II actually is one of the, with CMS, I was about to talk as CMS in a point of view of flavor physics, is well represented in India, and you have all this group involved in those measurements. So to catch up a little bit with the previous measurement I was talking about, I just mentioned about the lepton flavor violation in B2SLL. So I talk about limit recently obtained by Belle and LHC. So I will let Guy mention about the result from LHC. In this sector, for example, here the paper of Sorab on the search for a K star mu E bring us to the 10 to the minus 7, whereas you know, LHCb will have has already an edge for those mode. So this was done a little while ago, a few years back, and now the LHCb improve beyond those limit, but they are still important milestone for the for Belle, and obviously for Belle II with 2 order of magnitudes, you will reach 10 to the minus 8. And also I mentioned that's the plots I was showing earlier concerning those measurement of RK with in beam of Q square, the invariant mass of these 2 leptons. And this is for one of those beams in the 2 left plots where you see K plus mu versus K plus EE, and the control sample, the same final state in the JEPSI Q square beam. And yeah, where I was emphasizing that we do quite well with the electron, and actually you see from the yield have the same strength. So this is really the power of the B factory. So we'll need this Belle II statistics, but it's now easy to extrapolate with the state of the art of analysis, the best we could obtain. And as I said, the first Q square being information, that was analysis made by Seema Chaudhry from Hyderabad. So for rare decays, well represented in India, I took the opportunity here that, well, very often we say that, Belle can do B plus B0, whereas, on top of it, LHC B add B sub S and B sub C and lambda B and so on. But actually, we can also study B sub S. And here, this is an example of rare decays, always looking for loop, always looking for a diagram where it can be hidden the new physics and enhance those branching ratio. Here you have an excellent example of B sub S physics. B sub S physics in neutral to gamma, B sub S to 2 gamma, and you play the same game. You have the control sample on top of it just to validate and to demonstrate that you can do B sub S physics very well. So what you do is we talk about epsilon 4s. So to create this B sub S, or the opportunity to produce B sub S, you have to increase the energy of the beam and reach, in fact, in center of mass, the resonance we call 5s, or here in terms of energy, so 10.9 GeV almost. And you see no signal and can derive a limit on 10 to the minus 6. Of course, over there, the cross section is much smaller. So we have a much, almost 10 times lower cross section in B sub F than in B, but you have enough data in Belle to get the world leading measurement. And that's what's down here. Guwahati, sorry for the spelling, by Deepan Vita, and again an illustration of the possible analysis to be made and leading measurement shown and compared to other experiment. Sorry. So I was talking about B sub S. So with the same final state, you can do also D to gamma gamma, and this was done this time in TIFR. So you do the same thing, rare D decays. I mean, we focus on rare B decays, but though the interpretation might be a little bit more difficult in charm sector, this is also the opportunity, as I say, to probe those final state with a neutral, and here also give a leading measurement I show here, an illustration from the paper of NISER here. Okay, and just quickly here also, for the tau physics, we were talking about lepton flavor violation, and those are definitely some effort which will keep going and keep constraining new physics model. And of course, there is when I say golden mode, like tau to mu gamma, which are often advertised, or tau to 3 muons, and where again, I mean, Belle is really leading with here it helped by the very clean environment and the fact that there is no irreducible background most of the time, that at least for the 3 muons, for example, you can over the 3 electrons, you can almost be background free for a lot of those limits. Sorry, say it again. Okay, that's just. And from Belle to Belle II, you know see here, those are the limit expected with the full statistics of Belle II, and even so, just to give an example of what has been done in India, this is a quite recent paper here from TIFR colleagues, Decays, and this is a perfect illustration of the power, or let's say the advantage of Belle and Belle II over LHCb. LHCb had first put a limit on 10 to the minus 7, but suffering, I explained last time in the previous slide, by a very difficult background at lower mass compared to the B. It's much more difficult and struggle to reduce the background, the competing background, which is typically charm decays at the same around the same mass than the tau, as you know, around 1.8 GeV, and the difficulty of completely removing this background, so a sizable background which deteriorate finally their performance, whereas in Belle, even with current 1 inverse autobarn and 1 inverse autobarn sample, you can see that you immediately take lead with 1 order of magnitude. So there is a nice, in some sense, nice complementarity here, in the sense of we bring more, stringent limits, and they are listed for those modes which are not only lepton number violating but also baryon number violating, with a proton in the final state, and the lepton being either electron or muon or combination of it. So you have 6 modes, and this is the clean environment, the signal box in red, and as you don't see much signal, you are able to put those limits in 10 to the minus 8. So yeah, many more observable in rare BDKs can be probe, many more final state. And though, I mean, after it's a matter of interacting with theorists and looking for interesting mode. I'm talking about B physics, rare B, for lepton flavor violation. I was talking about tau just now. I can mention also epsilon effort, and here there is a good, I think I put the reference earlier, by I passed it, a very good effort in IISer Mohale from Sura recently, paper accepted for an epsilon 1s to any combination of lepton, including the tau, 1 tau. Okay, so for last part, I wanted to go on precision measurement, and especially concerning the CP violation. We are more in the first beam in some sense. Here, the standard model often in CP violation in B, as you probably already know, is quite large and has been observed in the B factories. And now I just quickly explain what is, the future of those measurements and what is the idea behind it. How do you bring some new physics back in the discussion? So just as a very quick introduction, and so when you talk about CP violation, you talk about interference, and to see the effect, to see the weak phase difference between 2 amplitudes. So you need to take a decays here in this illustration of the B2, the famous B2 Jeb psi. So the interference is made, so you have the same initial state, the B0, and the same final state here, Jeb psi K short. And the difference between the 2 paths actually give you this weak phase difference. So the 2 paths here will be the direct decay, So the color suppressed decay B to CC bar S. And the second pass will be actually through, because the B0 and B0 bar give the same decay, will be going through mixing. So B0 to B0 bar and B0 bar to J psi K short. And this VTD term in the diagram, this is what brings the sensitivity to sine to beta. And because this is mixing, so it's a time-dependent analysis, and mixing is changing, so B0 bar, B0 bar B over the time. And so you see the asymmetry, in fact, B0 versus B0 bar here in function of the time. And I just in next slide explain what I want to say. But you know, as an illustration, your asymmetry dependent of the time in the lower plot is actually changing over the time, and this is how you see this sine term, if you want, is this S term. So if it's different from 0 compared to the right part, then you will see CP violation, and you are measuring sine to beta. And this was really the legacy of Belle and Babar. And here, just as an illustration over the time since the very beginning, you see that, you know, this S term, this sine to beta, is well away from 0. So 0 is somewhere in the bottom here. And very quickly, with modest statistic, you start to see a departure, clear departure from 0. But as you want to do precision measurement with additional statistics, you get a quite precise measurement. On the right part, I mentioned at the beginning that epsilon 4s allow you many advantage in the rare BDK search, that you have 2B and nothing. So once you reconstruct fully 1B, the rest is your the decay of your signal. But in this case, the information you will take is the fact that you have, before any of the B decays, you have a coherent state. So when you have you tag a 1B, you know that at the same time the other is a B bar. And this is this information, and that also this asymmetry is used to actually to displace, in fact, to boost forward the 2Bs and to have a separation of the vertex. And the delta T I was talking about, the decay time difference between the 2B, it translated in a delta Z, a separation, so the distance between the 2B vertex as written here. And so what you're going to measure experimentally are those two vertex and this separation. So the horizontal axis I had in delta T would be delta Z. I show also a flavor tagging. So how do you know the flavor of 1B? So you look at kaon and muon or lepton in the final state, and the sign, the charge of those particles belonging to the B, the tagging, flavor tagging B will give you the flavor of the B. And one of the, you know, the performance of this flavor tagging is given by this effective tagging efficiency. And just as a comparison, you can see here again the fact that you reconstruct all the final state in clean environment, or most of the final state in clean environment, give you a large power of determining the flavor of the B. So you know at this T2, because you know the other B flavor, so you know the signal side flavor, and then you just have to reconstruct the J psi K short when it decays, and this this delta Z difference will give you the delta T. So very powerful tagging efficiency, which play a significant role, especially when you compare to LHCb. So LHCb has this few order of magnitude bigger sample, but then for the J psi K short, let's say, suffer from the K-short, lower K-short efficiency reconstruction, and suffer from the effective tagging power. And just as a comparison here, this is 1 order of magnitude, so the equivalent of 2 order of magnitude sample, if you want, I mean, in your race for precision. So this is the really powerful, that, you know, having a lot of statistics is one thing, and it's very good, it's very important, but also the quality in some sense of the data you take, or the efficiency and the lower background is the other side of the quest, in the sense of you need a clean samples, and you need samples with a high efficiency of tagging, of B tagging, of flavor tagging. Here you can see just how clean is a JEPSI short in B factory. And in fact, if you plot this decay rate of a B0 and B0 bar, you already see that you will have a clear asymmetry. The distribution almost are background free. So if you plot, here they are background subtracted, but if you do the same thing with a raw distribution, just plot this delta T distribution in function of the flavor of the B, then you would see clearly a separation. So you know that the asymmetry will look very well like CP is violated. And why I talk about this mode, because here, this is really one of the ultimate precision you will reach with Belle II. You can see that still, though very precise, almost when you combine B factory result in order of almost 2% precision, but still actually statistically limited. And so this means that Belle II can improve. It can also improve, so more effort will be will be necessary to reduce the systematic here from Belle II, and you know, be finally dominated by the systematic, and you know, after that probably this is the end of the road. But this will serve as a, you know, one of the most precise measurement and reference in the global fit of the unitarity triangle. So new physics enter when you try to measure this S term. So you do similar. So this was, let's say, the reference. So this was a JEPSI K-short reference, standard model dominated. And you will look at other decays, especially those penguins, so gluonic penguin, where you have a B0 to typically 5K0, 5K short, 5K long, or eta prime K short, eta prime K long. And you measure, I mean, you do exactly the same measurement and see if there is a discrepancy compared to the sine to beta you measure in JEPSI K short. So this is your reference, and this is the measurement you will do, the family of modes you are interested in, and you measure this S term, and you call delta S the difference between what you measure here and what you measure in B2 CC bar S. And those are the measurement, but at this stage, as you can see, still, you know, so far from the precision of the JEPSI K short, you are more in 10, 20% or more precision. And to go further, you need much more statistics, and that will be basically the one of the main purpose of the Belle II. So you see here as an illustration the case of eta prime K short, where you would have, for example, a departure of 10-15% in the value of S, and with a statistic of 15 inverse at 1, you would see very similarly, it's also a clean mode, so in blue compared to red, a clear departure, and you will be interested by, you know, compare it to the theoretical prediction. Here you have a summary, quick summary of other possible mode, and the sensitivity you will have with these statistics. And of course, you might have some contamination, theoretical contamination from other contribution, especially the charmless decay, B2U. And this, we will play the game at this precision to compare the measurement of the different mode and try to understand the pattern. And this is often actually the key out of the difficulty of disentangling other effect, is to measure the same observables in different final state and compare to the theory, and try to, with a combination of those observables, cancel, if you want, some of this pollution. Okay, so yeah, you can, I will go very quickly through, but you can play the same game here. It's very interesting because I wanted to illustrate one case where the rare B, so you remember the radiative I was talking about, where I was saying that, well, for the branching ratio, we are at the end of the road in terms of precision, but there is other observation, including CP violation. We have seen the direct CP violation, so typically B plus versus B minus for K star gamma. And here you can do the same measurement than sin to beta, but this time with a mode which is a penguin, and this will be typically so B2S gamma, but here the final state is K short pi 0 gamma, because you want to have access to this interference. Because the photon here in B2S gamma is mostly left-handed, so you don't have interference between the two, and consequently expect to have a S equal 0 this time, and the departure from 0 will help you to, will help you to prove new physics. And yeah, here again, at this stage of Belle, we have barely statistic to observe the signal. So we did, and we start to measure with a very large uncertainty. And yeah, you need this, again, large sample. And this is also one of the target of Belle 2. So another, I was talking about direct CP violation, and another angle you can measure is a gamma angle this time. And I'll show as an illustration the here the diagram involved. So again, the same game. You look at the weak phase difference between two diagrams, and you find a B minus to D0 K minus in two paths. One on the left side, the color allowed one, and the color suppressed on the right side. And the VUB here brings you the sensitivity to gamma. And this is basically the VUB angle. You need interference, and the typical way to obtain it is that the D0 and the D0 bar decay to the same final state. And that would be a typical CP mode, can be accessed by both, like a K plus K minus or K short pi 0. This is let's say, the simplest form of it. Of course, your CP violation effect, as you can see it from intuitively, will be proportional to the ratio of these two diagrams, and this ratio is called R. So the fact that R is close to 1, then you have a maximum interference, if you want, and so maximum sensitivity to CP violation. You can play the game. So R here, this ratio between those two diagrams is typically in order of 10%. This is not perfect. You would like to be larger, but this is much larger than many other modes, and give you the sensitivity to measure gamma in those modes. And D, I mentioned to K plus K minus and K short pi 0, but you have a different combination of B decays and charm decay, so it comes in many possibility. And for the asymmetry, as I mentioned quickly, but I put the material here, if you want to go through and you're interested by the subject. But gamma measurement is led by LHCb effort these days, and I'm pretty sure that the guy who is an expert of the field will give you a full information on it. So I will not spend too much time. And I said most of what I wanted to say on the subject, and I just go through quite quickly here. The asymmetry you are measuring, as I was telling you, allow you, so here asymmetry you can measure with different final state are sensitive to this gamma you want to measure, but also in the strong phase difference and this RB term, and all can be obtained in your measurement because you have enough observables, asymmetry, and the double branching fraction ratio to access to those observables. And again, so depending what final state you are looking at, you have different name of different theorists involved in this proposal, and this has been tried in B factory, Babar and Bell, and but the current precision is led by LHCb typically in order of 4 degree for combining all the possible information. One of the most sensitive mode, and here I go back to my list of contribution from Bell II Indian colleagues to this quest of gamma, is one of the, if not the first, the first measurement of Bell combined with Bell II data, and has been performed by an expert in gamma in Bell II from Madras, from Niharika, very recent paper in Dighe. This should be a J here. And you see, this decay sample growing. So here, this is a one of Bell, and with a more modest Bell II data sample, adding some sensitivity. And typically, the level of precision of the Bell plus early Bell II sample is in order of 10 degree. So this plot want to illustrate the fact that, LHCb is somewhere around 4 degree, and we are slowly try to catch up, and with the statistics, you should be quite competitive, but you need for that, something like a few inverse atobar to get back to the race. I mentioned Niharika paper, a lack of time, but just to illustrate, sorry, it should be a gamma here. It's also some effort made over many years, and you see here other contribution from Madras group where D explore some new decay, like in K short pi plus pi minus pi 0, which is a first measurement here, or some challenging final state like K pi pi 0 at the time, at the very early time of a Bell measurement. But you can see that, at least we have exploited as much as possible our data in the sector. Here, you can combine both this, kind of sensitivity through the mixing. So you take a B0 state, a B0 which go to B0 bar, and a very similar then a decay, so involving a gamma, so a B2U transition. So you find it in the B0 to D star pi final state. And here, if you want, you have a combination of what I was talking about, this first part of sine to beta, the second part of gamma, so sine to beta plus gamma sensitivity. But here the ratio, this R, this sensitivity is very small. We were talking about 10% for gamma. Here you have more, an order of magnitude smaller. So you have a tiny effect, which is very challenging. So a very large statistic of the sample, because you are back to the dominant mode we were talking very early. So this is branching ratio typically of 0.5%. So this is the statistics you want, but the effect is very tiny. And you don't have the sensitivity to the R term, so you extract only this S term, a combination of R and the angle you are interested in. And to disentangle this effect, you need to call other decays and combine those information to extract the full sine to beta plus gamma. This was an effort made by Sima Bahimpati a while ago already, and effort also a very nice synergy with other group of India and TIFR. Measuring this branching ratio, you need to complete the measurement. So I found it also the very nice illustration of, when you look for something, you often need additional information. And I was talking about different final state, which allow you to over-constrain your system and to disentangle the penguin pollution, for example. But also in this case where you need a QCD term, or you need a better knowledge, then you involve other branching ratio measurement here, B to D sub S pi or D sub S star pi, which were performed in TIFR. And I find this very nice illustration. I talk about CP violation in B sector. Here also, I mean, probably Guy will talk about CP violation in SHARM. So the measurement is done by a first observation in LHCb through, in fact, to cancel some of the systematic. What you measure is K plus K minus versus pi plus pi minus. And delta ACP, so the asymmetry you observe is compare. So the difference, I mean, you see the effect because it's different from zero with quite a significant way. So well away from zero, and you claim a first observation of the CP asymmetry. You see that, for the previous measurement in B sector, we were talking about R in level of 10%. So typically asymmetry of 10%, whereas you see this asymmetry is super small. So you need the full statistics. Those are sample of, several million of events. You see it's a log scale with 10 to the 7 here for the KK sample. So you need a huge statistic to measure this, and you understand that it's systematically limited, and consequently you need those trick as a difference of observables to cancel as much as possible the systematic which is common to both decays. And this was a very recent result a couple of years ago. And to explain if this is consistent with the standard model or it's a possible new physics, you need to have the full pattern of CP violation in SHARM, and you need to involve some final state which are a bit more delicate at LHCb, and the competition get back. Especially if you want to measure the 2 pi 0 pi 0, this can be done very nicely at B factories, or even D to K short, though here you have also competition from LHCb. So those, again, in one slide, I show here that those are different final state bringing different contribution. And then once you will have the sensitivity to measure all those asymmetries, then you will be able to solve the puzzle. I mean, or hope to solve the puzzle and see if on top of the standard model, you would have some new physics contribution. We have done a large effort in Belle, and this was led by people from TIFR and Bhubaneswar here, taking advantage of this easier at B factories mode, and to measure those asymmetry at less than % precision. and with final state which are not that easy. And so this was an effort done in 4-5 years back. Okay, so I think I'm at the end almost of these lectures. Guy had mentioned also that we have flavor experiment, but there is also good opportunity to probe spectroscopy. And I couldn't resist to show just a couple of slides on the subject. So those data allow us to probe for charmonium state or charmonium-like. So there is a lot of exotic states in the charmonium sector. And those are probed through different possible decays at the B factory. So of course, it's E plus E minus collision, so you can produce them directly with, at any energy when, through initial state radiation here, but also within the B decays. So one of the trick is to over constrain your system. So what you do is you reconstruct a B decay a bit similarly that what I mentioned for JEPSI K-short. But instead of JEPSI, you can take any final state and look for more exotic charmonium. And this has been also the playground of our Punjab colleagues. And here I just list some of the result obtained, some of the leading world leading result obtained with those technique, and Vishal and collaborators from Punjab have done an extensive effort using these BDKs, and you see it with one typical famous charmonium-like particles, 3872, with different final state in BDKs, and taking advantage of the good performance of Belle with final state with gamma has probed many interesting final state and make a very interesting discovery and very well cited paper. So again, this shows how vibrant and how active are the Belle II community, the Belle II community in India. Okay, so I'm now ending. So my first lecture and consequently my lectures in this school. And I hope I convince you that Belle II, as Belle, is not only a flavor factory, but has a very rich physics program. We have focused a lot in the BDKs because it's a special place to make those studies with special strengths, which compensate most of the time of just brute force statistics. And but it's also a charm factory. We talk very quickly about few charm possibility in CP violation and rare decays, and even more importantly, a tau factory, which is unique place to study tau physics, and which has a huge impact on indirect search. This is probably one of the nice sector to explore these days. So there is other things I didn't mention related to G-2, for example, for the muon. So this has a measuring cross-section, hadron cross-section E plus E minus is a very important element. Flavor physics often comes as a combination of observables, and you have to have a broad perspective to go from one sector to the other to collect all the observables, to constrain systems and to constrain new physics. And finally, dark sector I didn't talk about, but there is also here E plus E minus to many a portal to this dark sector environment. Okay, and the last slide is now for me to to show the statistics, the current statistic of Belle II, we started to take data in 2019, and you see that now we have equivalent. So this is the plot of last night, the equivalent of almost Babar-like experiment of 400 inverse femtobarn. Taking data until this summer, we should be very competitive with all the Belle measurements. So it's time for us now to get serious and to really provide to the world new set of results and push for a much higher statistics. We have a long way to go, and hopefully with this really open a new window to our quest of new physics. Okay, that's all. Thank you.
Thanks, Karim. So quiet audience today. Any questions for Karim, of having showcased various things the Indian community have done over the years?
I guess this last set of slides will allow you also to interact with your colleagues in India, because I mean you have basically a map of what is done and being done. I should have done at the end a map with the list of the expertise, but I think that wherever you are in India, you are a few hundred kilometers away from the Belle II sector. So
maybe next time we can have, despite of Gamma Thali, we can have Belle II Thali, something like that.
yeah, I'm trying to transform, but you know the slide, so I couldn't change it. Recycle the slide, yes, exactly. And yeah, I know that you have already sent me a message that I should mention about botamonium, but yeah, I mentioned just botamonium for the lepton flavor, recent lepton flavor, which I think it's a nice effort, but there is also classic botamonium study, and I didn't cover here. It's among the many other things we can do. Next time I will do a botamonium, or Sora will give the botamonium lecture.
Yeah, I know we've stayed away a little bit from spectroscopy in this.
Yes, exactly. That's why I just put what was enough, right?
That though it's related, it warrants a school of its own. It's got a very different set of things. Okay, so I don't see anything, but thank you very much, Karim, for